All right, hello chemistry students. Let's look at another chapter here in chemistry. And if you remember, we talked a little bit about states of matter in a previous chapter. We looked at solids, liquids, and gases. And in this chapter, chapter 11, we're going to dive into gases a little bit more and focus on some of their properties because there's some remarkable things that we can learn from gases. We're going to look at the pressure that gases exert. So we're going to be focusing on that a little bit. We're going to be looking at the relationship between volume, temperature, and pressure, and actually the number of particles for a gas. We're going to be looking at what we call, if we combine all of those relationships, what we call the ideal gas law. And then we'll touch again on diffusion and effusion a little bit. Those two topics we've mentioned before in the previous chapter. So let's dive right in. Let's look at some more fun chemistry and learn a little more in depth about gases. First thing we want to do, as you're taking notes here, let's write down section 11.1, and our topic here is gases and pressure. Okay? The first main point that you want to understand here is that collisions of air molecules, or any gas molecule for that matter, are going to generate pressure. Okay? So collisions by gas molecules. Remember, gases are moving, constantly moving, and they're moving very randomly, and they're moving more or less individually, okay, for an ideal gas. And when they bang into something, when they collide with something, they're going to exert a pressure. And if you've got millions and millions and millions of those gas particles, well, they're going to exert sometimes a significant amount of pressure. Okay? That pressure is what keeps your tires inflated. That pressure is what you feel. Actually, you may not sense it, but that is what you are experiencing from the atmosphere. So let's just make sure we understand what pressure is. Okay? Pressure depends on force and area. Here's a nice little illustration for you to understand it a little bit better. The actual calculation for pressure is you would take the force that is being exerted and divide by the area of that force, the area that is being exerted by that force. Okay? It is the force per unit of area on the surface. Now, here is to help you understand how the area and the force are related. Let's look at this example here. In this example, the force is 500 newtons. That is because of the weight of this individual, okay? The weight here, her weight is a result of her mass times the gravitational pull on her body towards the center of the earth, okay? So we measure that. It's measured in a unit called newtons, and right now her force, the force of her weight on the surface right here, is 500 newtons. If she is standing with both feet flat on the ground, let's say that the area of the bottom of her feet are 325 square centimeters. Area is measured in square units. So we would just take her force due to her weight, 500 newtons, and divide by the 325, and we get 1.5 newtons per square centimeter. That's the 500 divided by the 325. Okay? Well, if we continue here, let's say that she's not standing on the 2 feet here flat, but she's on her tippy toes on both feet. So this is obviously a ballerina, let's say. Her weight is not going to change, so the force due to gravity on the mass of her body is not going to change. That's still 500, but the area on which she is in contact with the surface is going to change. Now it's much less. It went from 325, now it's down to 13 square centimeters. So again, if we take 500 newtons and divide that by 13 square centimeters, obviously you're going to get a larger number. As this bottom area decreases, the denominator decreases, this is going to be larger. So if you take 500 divided by 13, this number right here is going to be much larger than the 1.5. Okay? You can do that on your calculator. Okay? Now let's say she should stand on 1 foot, on the tippy toes of just 1 foot. Now her area is only 6.5. So again, if you take the force due to her weight there in newtons, 500 newtons divided by 6.5 square centimeters, this number is going to be even larger than the previous two. As this bottom number gets smaller and smaller, the pressure that is being exerted by her weight is going to get larger and larger. Okay? And you know this intuitively because you can imagine, let's say, here's a good example. Let's say that you had a nail, and the tip of that nail is very, very small. Well, the tip of that nail, if you were to pound on it, is going to exert a lot of pressure, so much pressure that you can pound a nail into a piece of wood. Why? Because the force being exerted on that nail is going to be a certain amount, but it's also because the area of that nail on the surface of the wood is so small that the pressure exerted by that nail is quite extreme, and you can pound a nail right into a piece of wood. Okay? So yes, pressure, the greater the force, the greater the pressure. But also, since the area is in the denominator, the smaller the area, the greater the pressure. Now, this is a good time to talk a little bit about looking at this formula, as we're going to be looking at a number of formulas, and the relationship here between these three variables. So, pressure will go up as force goes up, okay? But pressure will go up as area goes down. So if it's in the denominator, if the denominator gets larger, the pressure is going to decrease. But if it gets smaller, the pressure will increase. So if our pressure goes up, if one variable goes up and the other variable goes up, then that is called a dependent. That's called a direct. That is called a direct relationship. Okay? That's called a direct relationship. If one goes up when the other goes down, that is inverse. That is an inverse relationship. Okay? Or you could say indirect. These two terms here we're going to be using as we look at pressure and temperature and volume and number of particles for gas. Okay? Alright, so that's your introduction to pressure as we talk a little bit about these relationships and how we find pressure, force divided by area. Now, as mentioned, a Newton is a force, and that force is that's the unit that we use for force. Okay? So we can talk a little bit more here and get into some physics. It actually is taking, it's the force that will increase the speed of 1 kilogram mass by 1 meter per second each second. Okay? So we'll just leave it there, since we just need to know that a Newton is our unit for force. Okay? But the idea here is, if you were to take a certain mass and increase it, accelerate it, then the mass times its acceleration is going to be a Newton. Okay? Now, you experience this every day, okay? But the idea here that we want to talk about next is that atmospheric pressure is something that you experience every single day. You don't think about it, but this concept right here of atmospheric pressure, all right, not just pressure, we talked about pressure here, but now the pressure from the air particles in our atmosphere, you are experiencing pressure from that all the time. So you are standing on the surface of the earth, okay, And above you are all of these air particles. The atmosphere is above you. There's a column of air above you on your head and on your shoulders, and that is exerting pressure. Why? Because those gas particles are bouncing off of your body, all right? Or you could say the weight of those air particles are resting on the top of your head and your shoulders. So there is what we call atmospheric pressure due to the gas particles in our atmosphere. Okay? And that pressure is exerted on the Earth's surface, and since you're on the Earth's surface, it's going to be exerted on you as well. Well, how much is that? 1 atmosphere of pressure is the force of 10.1 newtons. Again, that's the weight of the air particles, the pressure exerted by the air particles on 1 square centimeter. Okay, so on each square centimeter of the top of your head or your shoulders, there's going to be 10.1 newtons of force being exerted by those gas particles. Okay, so the idea here is that that's equivalent to a kilogram, nearly 1 kilogram sitting on every square centimeter. So if you just had a square centimeter here, it's not very big. A square centimeter is pretty small, okay? A square centimeter, resting on that square centimeter is a kilogram of mass. And that kilogram mass is being pulled towards the Earth's surface. The weight of that, due to the gravitational pull, is going to exert 10.1 newtons on that square centimeter. Okay? On that square centimeter right there. All right. Our atmosphere, of course, is made up of different gases. It's not just one gas. You've got nitrogen and oxygen and then other gases. Okay? Now, how can we measure that pressure? So, part C here, how are we going to measure that pressure? Well, that pressure is being exerted on every part of the Earth's surface and everything on the Earth's surface. So, if you have, this is one kind of rudimentary way to measure air pressure, and it was first devised here, as you can read, about, I don't know, in the 1600s or so, all right? And basically the idea here is if pressure due to these gas particles is being exerted by, or everywhere on the surface and on everything on the surface, if you have a bowl of water here, then there's going to be gas particles that are going to be exerting pressure on that water. Okay? And water will then exert pressure on the neighboring particles, and if you have a tube right here full of some liquid, it's going to exert pressure up that tube as well. Okay? And it will keep that water pushed up this tube a certain height as long as the air pressure, the atmospheric pressure, matches the weight of this liquid in the tube. All right? So the greater the pressure here, the greater the pressure on the water in the bowl, the more pressure is going to be exerted on the liquid in the tube, and it's going to push this liquid higher. It can match a greater mass or a greater weight of liquid in the tube. All right? If this atmospheric pressure is less, then this level of the liquid is going to go down. So we're measuring the air pressure by reading how much of this liquid is pushed up or is reduced, how much it goes up and down in the glass tube. Now, often that liquid there is mercury. Why? Because mercury is pretty heavy, so it's not going to go very high, and we can use a relatively small tube in order to measure the air pressure. All right? Or it might be some other liquid. But this is what we use in order to, traditionally, okay, what we use in order to measure the air pressure. Other methods would be used maybe today. But the idea is that gases are exerting a pressure. So if you have, here's another similar device. If you have gas in this sphere, and you were to open up these valves here, if you open that up, and in the other side of this spherical glass ball here, you have a liquid in this U-shaped tube. Here is your mercury, and the gas particles here, in this case they say they're oxygen. Those gas particles are going to then go through the tube once you open it up, and they're going to exert pressure on the mercury. And depending on how much pressure is in, depending on how many particles and the temperature and the volume of this sphere, as we'll see later on, those gas particles are going to push on the mercury, the liquid mercury. And it's going to push on this side, and it's going to push the liquid up on the other side. Over here, at the end of the tube, this is all just vacuum. There are no gas particles on this end. So there's nothing to stop. There's no pressure being exerted on this side. But all the pressure is coming from the gas in this container. So we push on this, and it goes up the other side, and we measure the difference between this level, and that is a reading in, say, millimeters, and that's why you see the gas pressure or the atmospheric pressure sometimes measured in millimeters of mercury. You're actually measuring how high this mercury is being pushed up the tube on the other side. Okay? All right. So that is a device that is used to, the manometer here. Manometer is used to measure the gas pressure of a specific gas in that container there, in that glass container. All right. Now we use different units for pressure, and you don't have to worry too much about all these different units, but I'll just give you a table that you can refer to. But just know that there are different ways or different units that we use to measure pressure. Pressure is still calculated the same way. It's still force divided by area, but there are different units that we use. Like, for example, we have different units for temperature, Kelvin, Celsius, Fahrenheit. We have different units for pressure as well. Okay? So as I mentioned, the common one is millimeters of mercury. You're measuring in that U-shaped container the difference between one side of the U-shaped tube and the other side on how far that mercury gets pushed up the other side. Okay? And that difference right there is measured in millimeters, and since the liquid in here is mercury, we say it's millimeters of mercury. So that's a common unit for pressure, for atmospheric pressure. Okay? Now also, 1 millimeter of mercury is also called a torr. So 1 torr and 1 millimeter of mercury are exactly the same thing. All right? If we want to use a different unit called atmosphere, 1 atmosphere, abbreviated ATM, is equal to 760 millimeters of mercury. Okay? And the reason that's used is because that is the average atmospheric pressure at sea level when it's 0 degrees out, 0 degrees Celsius. So we kind of use that as a standard. 760 millimeters of mercury is kind of the average air temperature, or sorry, the air pressure, the atmospheric pressure at sea level when it's 0 degrees. And so we just say, well, that's going to be 1 atmosphere. Okay? And then there's another one there called the Pascal, and that's equal to the pressure exerted by a force of 1 Newton acting on 1 square meter. All right, and you can kind of see those are standard values there. All right? So this table here is showing you basically, if we want to look at the standard temperature and pressure here, these are showing you the different units, and you can refer to this table. So as I mentioned, there's your Pascal, there's the millimeters of mercury, there's the torr, there's the atmosphere, and then one more, and this is more common obviously in the United States, pounds per square inch. You'll see on the side of a tire, you'll often see the unit here for pressure. The air pressure in your tire is in pounds per square inch. Okay, so instead of newtons, pounds, instead of square centimeters, it's square inches. Okay? Now, we often want to kind of use a value at standard temperature and pressure, or temperature and pressure. So those are called standard temperature and pressure that we use to kind of have something relative to measure it against. is 1 atmosphere and 0 degrees Celsius. Okay, so if you're taking a measurement and that measurement is happening when it's 1 atmospheric pressure, the atmosphere around you is at 1 atmospheric pressure, 1 atmosphere I should say, and the temperature is 0 degrees Celsius, and you're measuring other things, we say that measurement was taken at STP, standard temperature and pressure. That's what that stands for. STP is standard temperature and pressure. What is the standard temperature? 0 degrees Celsius. What is the standard pressure? 1 atmosphere. Okay? So it's for uses of comparison, we can compare using the STP, as you'll see later on. All right. The other thing that we want to talk about in this chapter is called partial pressure. As I mentioned, in the atmosphere, there's a mix of different gases. So you've got nitrogen and oxygen, and then other gases as well. And each gas, each particle is exerting a pressure, but each gas has its own pressure. And so we're going to add up those different pressures in order to get the total pressure exerted by the atmosphere. So we can measure what's called the partial pressure of each of the gases. So the pressure exerted by each gas in a mixture is called the partial pressure by that individual gas. All right? So this is an important concept. It's really a simple calculation. You're just adding up all the individual pressures of each gas and then getting the total pressure. But the total pressure is the sum of the individual pressures, the partial pressures of each gas. Okay? So that is often referred to as Dalton's law of partial pressures, and this is a simple calculation. P sub T stands for the total pressure, and then each individual gas has its own pressure. We just add them up. That's that easy. Okay? And then finally, we just want to talk a little bit about the procedure that we will use in a lab to collect a gas that is going to be a product in a reaction. So let's say that we have a reaction happening in this flask right here, and one of the products from this reaction is a gas. Well, that gas would normally, if we don't trap it, is going to be escaping into the atmosphere, and we would never be able to measure it. So we close and we put a stopper on this flask, so when the gas is produced, that gas then is going to come out this tube, and it is going to be bubbled. This tube then goes into this container that has water in it, and it's going to bubble, and it's going to start to create a area here, or volume actually, where this gas is being collected, and it's going to push the water down as more and more bubbles come up. All right, this is a closed glass container. So in this volume up here in this glass container where we are collecting the gas, you're going to have, let's say that hydrogen is the product that we are producing from this reaction over here, you're going to have hydrogen gas particles. Okay? Hydrogen gas particles. But also, because this is being collected above water, you're also going to have some water vapor. There's going to be some water vapor there as well. There's going to be both. Water was not one of the products from this reaction, but it's just a result of collecting this above the water. So this is called gas collecting, or gas collected by water displacement. The air, sorry, not the air, the hydrogen gas that we are collecting here is going to be collected above the water, and it's going to push this water, displace the water out of the way, and as a result we're going to have hydrogen up here, and then we can collect it, we can kind of measure it, we can measure the pressure of it, etc. But there's also going to be, as a result of the way that we're collecting the hydrogen, there's also going to be some water vapor. So this is where we have to use partial pressure. You have water vapor and hydrogen both up there, not just hydrogen, okay? And the pressure that is being exerted by water vapor, that's a known value. We can calculate that value, or we can look up that value. if we know the temperature. And so then we can use the water vapor pressure and the hydrogen pressure together would give us the total pressure that is being produced from the gas that is above that water. Okay? So the idea here is if we know what the total pressure is, and that total pressure, by the way, okay, this is open to the atmosphere, so the atmosphere is pushing down on the water here, so that is the atmospheric pressure, and the pressure inside here by the gas particles is going to match that atmospheric pressure. So these particles in here are pushing down on the water in the glass container, but the air particles outside are pushing down on the bowl of water here, and therefore they're matching each other. The atmospheric pressure is pushing up, the particles inside the glass container are pushing down, and they're going to match each other. So the more gas we can collect from this experiment, the more this water is going to get pushed down, and the more particles we're going to be collecting up there. Okay, but the pressure inside of this glass container are going to match the atmospheric pressure. Okay, so we would know that the total pressure inside the glass container that we're collecting the hydrogen gas is going to be equal to the atmospheric pressure, and that we can figure out. We can look that up on a particular day. And then the hydrogen, this is the one that we don't know, which we're going to calculate, but the pressure due to the water vapor is something we can look up because that's been calculated over and over at a particular temperature. So then we can find, this is a known value, known atmospheric pressure, that's the total, this would be your total, and the water vapor, this would be known. We can look that up on a table, and that allows us then to find the pressure due to the hydrogen. Okay, so the total pressure, the water pressure, and the pressure of the gas, whatever the gas is, in our case it's hydrogen, we can find the gas pressure, the hydrogen pressure, by knowing the water pressure and the total pressure, because we know the two gases, the hydrogen and the water, have to add up to the total. Okay? And this table is just showing you that the water vapor pressure is a known value. If you know the temperature at which the water vapor is, we just can look it up on this table, and we know then that the pressure is going to be a certain amount. And you can measure that in millimeters of mercury, which is a torr, or you can measure it in pascals, or actually this is kilopascals. Okay? There are 1,000 pascals in 1 kilopascal. Alright? So, for example, let's say that you were doing an experiment and you were collecting oxygen gas in the manner described earlier, okay, and you did this by water displacement. So, in this experiment, you're going to have a reaction happening. The reaction is happening in this flask. The oxygen is produced, and it is pushed through this tube into this container having the water, and the water is pushed out of the way. More and more pressure is going to be collected up here. It's going to be produced up here in the top of the container that has the water. That water is going to be pushed down, and the pressure that is being produced up here in the container is going to be equal to the atmospheric pressure pushing back up. So now, all we do is we look up the atmospheric pressure for the day, whatever that is, okay, and that's going to be your total. And then we know that total pressure is a result of the pressure from the oxygen and the pressure from the water vapor. There's always going to be water vapor in there because you're collecting the oxygen gas, in this case, above water. There's always going to be a small amount of water vapor. And so this total right here is the atmospheric pressure for the day. We just looked that up. Okay, it says if the atmospheric pressure during the experiment is 731 torr. So in the atmosphere, in the room where you are doing the experiment, it's 731 torr. And let's say we look up on the table, since it's 20 degrees Celsius in the room, and we look it up and we say, okay, 20 degrees Celsius, there it is. That's 17.5 torr as a result of the water pressure. Okay, so that's the pressure because the water vapor in the glass container where we're collecting the gas. And so all we do is we take, this is our 731, This is the 17.5 that we looked up on the table, and we solve for the pressure from the oxygen. Just take the 731 minus the 17.5, and it's 17.135, or 713.5, okay? All right, so that's how you use partial pressure to find the pressure of a gas. In an experiment, we're using water displacement method. All right. Now, here's the really cool part of this chapter is we're going to be talking now about, in section 11.2, the gas laws. And these are showing the relationships between pressure, volume, temperature, and then we'll talk about particles. So this is pressure, volume, temperature, and N is going to represent moles, or number of particles. Okay? So these gas laws are simple relationships. Remember I mentioned before, the relationships between these are either going to be a direct relationship or they're going to be indirect or inverse. Those are your two choices. Either when one goes up, the other goes up, or when one goes up, the other goes down. Those are the relationships between these four variables. Okay? Now, there are different relationships here, and I'll summarize them for you, and then we'll go through them, and then we'll make one formula at the end. One formula at the end will take care of all the relationships. Okay? And I'll show you how easy this can be. And these relationships are named after different scientists, as you can see. But there's a relationship between pressure and volume. There's a relationship between pressure, and this should be an N here, okay? Pressure and the number of particles. There's a relationship between pressure and temperature, and then if we put them all together, pressure, volume, temperature, and we're going to throw in number of particles there in a second, okay? All right. Let's talk about some of these different ones here. Here's the first one. Gas volume and pressure are indirectly, there it is, indirectly, indirect relationship, indirectly proportional. What does that mean? So as volume and pressure change, it's going to affect the other one. How? In an indirect manner. If you increase the pressure, that's going to decrease the volume of your gas, and vice versa. Now this makes total sense. You intuitively you would know this. If you have a balloon, okay, and you are somehow able to increase the pressure on the outside of that balloon, okay, you're able to push on that balloon with greater pressure, well, the size of that balloon is going to decrease, okay? Or if you were to reduce the pressure around that balloon, the balloon is going to increase. Remember we talked before about gas particles are compressible? Well, you can push, you can exert pressure on those gas particles, and you can push them closer together. That's all that's happening here. Increase the pressure, the outside pressure, the exterior pressure, and those particles are going to get pushed together. Decrease the exterior pressure, and those particles are able to spread out more. It's just that simple. Okay? So that's this relationship right here, pressure and volume. Pressure and volume are indirectly related. Now, let me just show you something really quickly here. When we have an indirect relationship, we can say that the one variable times the other variable is going to equal some constant k. This k is some constant. All right? Just think of real numbers. Think of real numbers like this. If you had 3 times 4 equals 12, okay, and this is the first number is 3 and the second number is 4, well, what if the first number increases to 6, but you want to keep the product equal to 12? Well, then the second number would have to be 2. So see how the first number went up, the second number went down. All right? First number went from 3 to 6, then the second number's got to go from 4 to 2. So as one number goes up, the other number has to go down. Okay? That is an indirect relationship, and you can express that by the product of the two variables is equal to a constant. In this case, pressure times volume is equal to some constant. Okay? Now that is called Boyle's law, and there's the relationship. And what you can say is, well, what if you have a situation where the pressure and volume change? And there's an initial pressure and volume, and then something happens, and then there's a second pressure and volume after a change. Well, we can equate the two products. If pressure times volume is equal to some constant, and then there's a change, then that initial pressure times volume has to equal to the same constant as the pressure and the volume after the change. So we can equate the two products. Just like I did over here with the simple numbers, if 3 times 4 is equal to 12, well, if the first number becomes 6, then the second number would be 2. So then 3 times 4 is equal to 6 times 2. Obviously, they're both equal to 12. And here's what's going to happen with us. You're going to know 3 of the 4 variables here. So for example, if I just keep, again, my very elementary example, if I give you this situation, if 3 times 4 is equal to 6 times something, what, you would be able to know that this something is 2. And that's exactly what we're going to do in these relationships. You're going to know, in this formula here, you're going to know 3 of these variables, and the fourth one you're going to have to find. Okay? All right, and this example here, if you want to pause this and walk through this example, it's really simple. Again, here are the 3 variables that you're given, and this is the one that you want to find. So if we notice that, what are they? They're volume and pressure. So we can use this relationship, Boyle's law, and we can plug in the values that we do know and solve for the one that we don't. And that's all that's happening here. Here are the 3 that we do know, and we're solving for the one that we don't. Okay? All right, second one. Gas volume and temperature are directly related. Okay, if they're directly related, what does that mean? Here we're looking at volume and temperature. This time, as temperature increases, volume is going to increase. That's a direct relationship. Okay? And what do we do to express that? It's going to be V over T is some constant. This time it's the ratio that's going to be constant, not the product. All right? Again, let me give you a simple example. If you have 2 over 8 is equal to a constant. Well, that's equal to 1/4. Well, if I had the top number to be 8, okay, then the bottom number would have to be, and if I want to keep the ratio the same, right, 2 over 8, if I reduce that to 1/4, 8 over what is going to also equal 1/4, if I want to keep this ratio exactly the same. And obviously the answer here is 32, okay? So the idea here is that a ratio, the numerator divided by the denominator, is going to be some constant. As the top number goes up, the bottom number has to go up. So 2, the top number went from 2 to 8, 4 times as much, right? And so the bottom number had to go up by a factor of 4 as well. They both go up in order to keep them equal to some constant. And again, like we did before, if you know 2 over 8 is equal to 1/4, and then you say, okay, well, what if the top number is 8? What would the bottom number have to be? This is, again, an example of where we're going to find some value. We're going to have to solve for something, knowing 3 of the 4 values. Okay? So this is volume 1 over temperature 1, and then there's a change that occurs, and we have a second volume and a second temperature, and as long as the pressure and the number of particles doesn't change, then we can equate these two and solve for the unknown, knowing 3 of the 4. Okay? All right. Then you can look at this example. This is doing exactly the same thing. See how you're given 3 and you're trying to find the fourth one, and you see that they're volume and temperature. So you use the relationship between volume and temperature and solve for the fourth one just by plugging in the other 3. Okay? All right, third one. Pressure and temperature. They are directly related as well. So as the temperature goes up, the pressure that gas is exerting is going to go up. So imagine, right? I mean, again, you know these intuitively. If you had uh, let's say a can of pressurized gas. If you ever seen an aerosol can that says, do not put them in, don't burn them, don't put them in a fire. Why? Because you will increase the temperature of the gas particles in that aerosol can so much that the inside pressure is going to skyrocket, and you're going to cause a possible explosion of the aerosol can. So as the temperature of the particles increases, and this relates to what we talked about in the previous chapter, if you increase the temperature, you're putting heat into those particles, they're going to increase their kinetic energy. And that kinetic energy is going to increase the pressure that they're exerting on the inside surface of that container, whatever container they're in. And that pressure is going to increase as a result of increasing the temperature. So as temperature goes up, pressure goes up. Again, as temperature goes up, pressure is going to go up. So pressure over temperature is going to be a constant. And just like we did with the other variables, we can equate an initial pressure, an initial temperature, and after something changes, the temperature changes, now we have a new temperature, well, we could find the new pressure. Again, you could find an unknown knowing 3 of those 4 variables. Okay? And this example is showing you exactly the same thing. Here we have pressure and temperature, so we would use this relationship. And you are given 3, and you plug them in, and you solve for the 4th. Okay? All right, I think we're on the 4th one here, right? Looks like it. All right. Now, we can take all of these and we can combine them together. So the 4th point here is that if we take pressure, volume, and temperature, and instead of looking at them in pairs, we're going to look at all 3 together. Well, remember what we had here before? If we know that some of these relationships are indirect and some of them are direct, we can combine them all into one. All right, so here, remember before we said that pressure and volume are an indirect relationship. We said that pressure and temperature is a direct relationship, and we said that volume and temperature is a direct relationship. Well, all we're going to do now is we're going to combine them all. It's pressure times volume. So notice in our combined gas law, it's pressure times volume in the numerator, and then temperature is in the denominator. So we put temperature in the denominator. And this relationship is a constant, PV over T. It even rhymes. How wonderful is that? PV over T is a constant. And just like we did before, we can say here is a situation before something changes, and here's after something changes. So PV over T for the first situation has to equal PV over T for the second situation. Now you've got all 3 variables. We're going to have 6 different values. 3 before, 3 after, and if you are given 5 of those, you should be able to find the 6th. Okay? You should be able to find the 6th. Now, here's the nice thing. If it says in the problem, listen carefully, if it says in the problem that volume is constant, then you would not need volume in this equation, and it would just be P over T. If it says that pressure is constant in the experiment or the problem, then you would not need the P in the formula, and you would just be using V over T. If it says that temperature is constant, then you wouldn't use the T in this formula, and it would just be PV equals PV for before and after. Okay? So if you use this one formula for all the different laws, you don't have to memorize 3, 4 different laws. You can just memorize this one or just know this one. If you know PV over T is a constant, that's all you need to know. Because Even if one of these variables is constant, then you just drop it out and just you have the other relationship for the two variables. Okay? So let's look at an example here. It says a helium-filled balloon has a volume of 50 liters at 25 degrees Celsius and a pressure of 1.08 atmospheres. This is before. This is the first situation. So this is your volume 1, this is your temperature 1, and this is your pressure 1. Okay? Notice we're given all three variables. So yes, you're going to use PV over T before has to equal PV over T after. Alright? So then there's some change that occurs. It says what volume will it have at this pressure? Now the pressure's changed and the temperature has changed. And we want to find that volume. So we are given, this is a nice way to set it up. What are you given? You're given the first pressure, the first temperature, the first volume. They're all there. Then you're given a new, here's number 2, a new pressure, a new temperature. That's your pressure 2 and your temperature 2, and you want to find volume 2. This is the one that you do not know. So you take your combined gas law, all three variables are being used, all three of them. So we plug them in, all right? Oh, by the way, we have to make sure that we're using the temperature here, and the temperature has to be in Kelvin, okay? So this temperature is given to you in Celsius, and all we do to get it into Kelvin, Kelvin is a measurement for temperature, and it's always going to be positive. In other words, 0 Kelvin is the theoretical value where particles stop moving. So that's 0 Kelvin is, there's nothing less than 0 Kelvin, because 0 Kelvin is when particles, there's no kinetic energy in the particles. A theoretical value that basically matter stops moving. Okay? So all temperature measured in Kelvin is always going to be above that. Okay? So how do you convert from Celsius to Kelvin? You just add 273 to the Celsius value, and then you'll get it in Kelvin. Okay? So we take the given temperatures, you add 273 to get them in Kelvin. All right? They always have to be in Kelvin when you're using the gas laws. And then we just plug in the values that we know. By the way, what we're doing here is we're taking this formula and we're solving for the unknown. So to do that, I'll show you really quickly here. We're trying to find this V sub 2. So I need to multiply by T sub 2 to cancel that on the right side, and then I need to divide by P sub 2 in order to cancel that on the right side. Then the V sub 2 will be by itself, and that's what this formula is right here. Okay? But you're just basically plugging in your known values. You plug in the pressure, volume, and temperature initially, and the temperature and the pressure after the change, and you solve for the V2, the second volume. Okay? And that's what's happening here. Notice the units here. Units are going to cancel for temperature, units are going to cancel for pressure, and you're going to be left with liters here. Okay? Notice that the volume, let's see if it makes sense here. The volume initially was 50, right, before anything happened. Then when the pressure and the temperature changed 50, it went to 60. So there was a slight increase. Well, it looks like what would increase that? Well, the volume increased because the pressure decreased, but the temperature decreased also. So it looks like the pressure had a bigger impact than the temperature did. Okay? But in any case, you just use the calculation and you'll find your new volume there. Okay? All right. In 11.3 here, 11.3, we're looking at gas volumes and what we're going to call the ideal gas law. Okay, remember, when an ideal gas is one that obeys all the assumptions of the kinetic molecular theory, the biggest one being that gas particles are not attracted to each other and that the collisions are elastic. not perfectly true, but it helps us with our model. Okay? So section 11.3, write down the ideal gas law. That's what we're going to talk about here. Okay? Okay, the idea here is that just like any substance, we talk about moles of that substance when we talk about a reaction in chemistry. So a mole is our quantity that we use, just like you use a dozen to represent 12. A mole is the number that we use. 1 mole is a huge number, 6.022 times 10 to the 23rd. Okay? So that's the value that we use when we talk about a quantity of particles usually. All right? So if you have a reaction, and let's say that all of these are gases in this reaction, so hydrogen gas and oxygen gas react to give you water vapor, okay? H2O in gas form. Well, the way that these react, excuse me, they are going to be in a 2, excuse me, they're going to be in a 2 to 1 ratio. 2 parts hydrogen always react with 1 part oxygen to form your water. Because look at the formula for water here. Not water, but hydrogen, water vapor. They're in a 2 to 1 ratio. So you always have a 2 to 1 ratio for hydrogen and oxygen to form your water. Okay? And we can talk about the number of particles. This could be 2 moles to 1 mole, and creates your water vapor over here, okay? Or, since gases expand and contract, we can also refer to this as volumes. We can refer to this as volumes, all right? So, in this case, we have a relationship between these gases in this reaction, and we can refer to them as moles, number of particles, or we can refer to them as the volume of that gas. All right? Now this is unique for gases. So the law of combining volumes of gases, it basically says that the volumes of gaseous reactions and the products can be expressed as ratios of small whole numbers. And again, as volume or as number of moles. Let's look at some examples here. All right, this was our first point here, and our second point now. So, equal volumes of gases under the same conditions are going to have equal number of molecules. It doesn't matter what gas it is. All right, let me just say that again. If you have hydrogen gas and oxygen gas, even though they have different masses, if they're at the same temperature, if they're under the same pressure, then guess what? You're going to have the same volume of both. Equal volumes of gases under the same conditions contain equal number of molecules, the same volume, and that means you're going to have the same number of particles, same moles. Doesn't matter what the gas is, okay? And that does have to do a little bit with the kinetic energy. Remember, when things are at the same temperature, they have the same kinetic energy. So this hydrogen gas and this oxygen gas are going to have the same kinetic energy. So they're going to be exerting the same pressure on the inside of the container, and as a result, they're going to have the same volume, and we can conclude that they have the same number of particles in there, okay? Now, the hydrogen gas, because it's lighter, may be going faster, but that's not what we're talking about here, okay? We're talking about temperature, pressure, volume, and number of particles. So this is a pretty neat relationship, because now we can bring in number of particles here. We talked about temperature, pressure, and volume. Now we can talk about moles as well, all right? Moles as well. So let's look at, now we're going to expand our formula to include N, which is going to be number of moles. All right? This relationship is sometimes referred to as Avogadro's law, and it's the relationship between volume and number of particles. So, again, will you be able to tell? Can you tell what relationship this is? If it's V equals K times N, where this is the number of particles, and this is the volume. It's not written the way that our relationships were written before. Remember, they were set equal to a constant. This is our constant. So all I'm going to do is I'm going to divide both sides by n. V over n is equal to some constant. So remember, this is a direct relationship. As V goes up, n has to go up in order to keep the ratio equal to this constant. So this is a direct relationship. So there's a direct relationship between volume and number of particles. Well, remember, volume is related to pressure and temperature. So now we can bring in all 4 variables now. Okay? So here's the neat thing. We have one formula for all 4 variables. All right? And then we can look at some examples here in a second. But I'm going to show you now what is called the ideal gas law. All right? Ideal gas law is basically relating all 4 of those variables. Now, one little side note here, that this is a nice number to know, by the way. If you have any gas and it has a volume of 22.4 liters under standard conditions, that means all gases are going to have that volume under standard conditions, and you're going to have the same number of particles for that gas as well. So this is called the molar volume. Molar volume. All right. So remember what the standard conditions are. It's 1 atmosphere and 0 degrees Celsius. So it doesn't matter what gas you have, because there's a relationship between pressure, volume, temperature, and now number of moles. We don't have to worry about what kind of gas it is. If we know that it's at 1 atmosphere, 0 degrees Celsius, then we know that there's going to be a known volume if you have the same number of particles for that gas, for whatever gas it is. And for 1 atmosphere, and molar, that's molar, the mole here, 1 mole, pressure here is 1 atmosphere, the temperature is 0 degrees Celsius, then this volume is going to be set. And what is it? It's 22.4. 22.4 liters is the volume of a mole of any gas at 1 atmosphere and 0 degrees Celsius. Okay? So we have now a formula that allows us to use and allows us to show the relationship between all 4 of these variables. All right, let's get to that right now. And then we'll do some calculations. All right, remember, these are our 4 relationships here. Now we're going to combine them all into one called the ideal gas law. The ideal gas law is showing the relationship between all 4, and here it is. PV equals nRT. Now I'm first going to show this to you in a different form, all right? So P times V, so P times V, and then notice, remember that T was always in the numerator, right? So we're going to have the T in the numerator, and then also you'll notice this is written a little bit differently than we did before. We wrote it as V over N. The N, V over N is a constant, the N is in the numerator as well. Okay? So if I took this formula right here and I divided by N and T to cancel those, N and T, R here is our constant. It's not a K now, it's an R, okay? Constant. So it's PV over NT is equal to some constant R. Or if you want to say PV equals nRT, that's another way to write it. Okay? PV equals nRT. Again, it rhymes. How cool, all right? But basically what we're saying is the relationship here between pressure, volume, number of particles, and temperature is a constant, and that constant is R. This R here is just a constant value. Okay? It's a value that is not going to change and has certain units there. but PV over NT is some constant. Or another way to write this is PV equals nRT. It's the same formula. It has all four variables: pressure, volume, number of particles, and temperature. Okay? And yes, you could have PV, you could have this set up where you could say PV over NT for the first situation, and then if there's a change, PV over NT for the second situation. And notice now we have 8 variables. We have 8 different variables, and if you're given 7 of those, you should be able to find the 8th. Okay? So you'll see right here, here we're given this relationship, okay? And we're saying here, well, what is that value? The ideal gas constant, that R, is just a known value. It's a constant. It's never going to change. Well, if I plug in a pressure, 1 atmosphere, a volume, 22.4 liters, and I plug in the number of particles, 1 mole, and I plug in the temperature, 273.15 Kelvin, sorry, and I evaluate this right here, I get 0.082. That is what R is equal to in liter atmospheres per mole Kelvin. That's what the R value is. That's the constant right there. Okay? Now, depending if we might use, instead of liters, we might use a different unit for volume. Or we might use, instead of atmosphere, we might use something different like torr or millimeters of mercury. So these units might be different, and then if they are, this value of R is going to change a little bit. So this table is just showing you different values for R depending on what units you use for pressure, volume, temperature. Okay, notice the temperature never changes, moles never change for those units, but depending on whether you use liters or cubic meters, or whether you use millimeters of mercury for pressure, or atmospheres, or pascals, or kilopascals, this R value is going to change slightly, okay? Or it's going to change because of the units, all right? So you would just have to, this is the one that we just talked about. This is the 0.08 using liters, atmospheres, moles, and Kelvin. But if you have different units, if you're using, instead of atmospheres and liters, if you're using pascals and cubic meters, then this is the R value that you would use. If you're using millimeters of mercury and liters, then this is the R value that you would use. Just refer to the table, okay? All right, now let's do a sample problem here. Let's walk through one and show you how cool this is. This one formula, PV equals nRT, takes care of everything. Takes care of everything, all right? Everything you need, all the variables, PV, N, and T, pressure, volume, number of particles, and temperature. Everything's taken care of. All right? So let's see what we have here. Let's walk through this one. What is the pressure in atmospheres exerted by 0.5 moles? This is our N. Pressure, P1, we don't know it. Nitrogen gas in 10 liters container at 298 Kelvin. So this is a volume, and this is a temperature. Okay? So there are your 4 variables. Well, there's a relationship between all 4 of those variables. And the relationship is PV equals nRT. PV equals nRT. So we are given the volume in liters, the number of moles, the temperature in Kelvin always, and we're asked to find the pressure in atmospheres. Notice liters and atmospheres. So what R value are we going to use? Liters and atmospheres. Liters and atmospheres, we're going to use the 0.0821 for our R. So we're also given the R value. Okay? And all we do is we plug these 4 variables, 10, 0.5, 298, and 0.821 into our formula and solve for the unknown pressure. And that's what we're doing right here. And you find the pressure, done. That's how easy it is. Okay? All right. And then we'll talk a little bit about diffusion and effusion here, but very briefly. So in this section, what we'll do is we will touch again on the concepts of diffusion and effusion. We mentioned these before. So I'll put down section 11.4, your heading, and we'll talk about them separately, and we'll talk about how they relate to the velocities of the particles, which again is related to the kinetic energy, 1/2 mv squared. Okay, so let's review just what they are. Diffusion, basically, is when you have gases that are mixing. So you can write down diffusion is the mixing of gases. And they will mix quicker if the particles are moving faster. Let's first of all just give you an example of diffusion. Really simple. If you had a bottle of perfume here, and you have oxygen and nitrogen in the atmosphere around it, you take and open that bottle of perfume, well, those particles of perfume, those particles, because it's a volatile liquid, it evaporates readily, those particles are going to evaporate. And because it is an open system, it's going to come out into the atmosphere. And because gas particles are constantly moving, remember the kinetic molecular theory, particles are constantly moving, they're not just going to all stay clumped up in one area. They're going to bombard each other, they're going to collide with each other, they're going to bounce off each other, they're going to mix, air particles coming this way, oxygen particles going that way, perfume going this way, that way. It's very random. And as a result, you're going to have a mixing of these different particles. The perfume particles, the oxygen in the air, the nitrogen in the air, the other particles in the air. That's diffusion. These perfume particles are going to continue to spread out, and even if you're standing far, far away, you're going to eventually get a little whiff of that perfume. Not far, far away maybe, but you know what I mean? You can be standing away from that perfume, and eventually you'll get you'll be able to detect that perfume scent. Okay? Now, as I mentioned, you should know this. The rate of diffusion, how quickly things mix, depends on the speed of the molecule. That should make sense. The faster they're moving, the faster they're going to spread out, the faster they're going to mix, and the rate of diffusion is greater. Okay? If two gases or three gases, however many, if multiple gases are at the same temperature, then they have the same average kinetic energy. Okay? But, as we've mentioned before, the gas whose particles have a smaller mass have to be moving faster. Let me remind you of this. Kinetic energy is 1/2 mv squared. If you have two gases and their temperatures are the same, that means the kinetic energies are the same. The two kinetic energies are the same. So the kinetic energy is like a constant. So 1/2 mv squared for the first gas, I'll put a 1 here, has to equal 1/2 mv squared for the second gas. Because the kinetic energy of the one, which is 1/2 mv squared for that gas, has to equal the kinetic energy of the other one. The kinetic energies are the same if they're at the same temperature. But these masses right here are different. Therefore, the velocities have to be different. If this mass is large, then the volume is going to be smaller than the second volume. Okay? If mass 1 is greater than mass 2, then volume 1 is going to be less than volume 2. Here's what it means. I'll say it again. The smaller mass particles are going to be going faster so they can have the same kinetic energy as the heavier ones. The heavier ones don't have to move quite as fast to have the same kinetic energy as smaller particles. Okay? So what does that mean? It means that particles that are heavier are going to diffuse more slowly. Okay? They're going to diffuse more slowly than lighter particles. Lighter particles will diffuse more quickly because they're moving faster. Right here, Key point, make sure you have this. The rates of effusion and diffusion depend on the velocities of the particles. Okay? So diffusion, remember, is mixing. It's mixing. Effusion is passing through a small hole. But the principle still applies. Both of these, effusion and diffusion, will happen faster if the particles are moving at a higher velocity. Okay? Here is exactly what I just showed you. This is the kinetic energy of particle A has to equal the kinetic energy of particle B. And I set the two equations equal to each other. And what we can do here now is we can compare the velocities. Velocity of A, velocity of B, those are the average velocities of the particles. I'm going to take this equation and I'm going to solve for the velocity of A over the velocity of B. If I do that, watch. Mass of A, velocity squared of A, and then do the same thing for B over here. Okay? I'm going to solve, I'm going to get the ratio of A over B, velocity of A over B. I'm going to write that as a ratio. So I need to get this velocity of B over onto the left side. So I'm going to divide both sides by the velocity of B squared. Cancel that. And then I want the mass on the other side. So I'm going to divide by the mass of A. That cancels. Mass of A. Okay? And then I'm going to divide both sides by half, and it cancels the halves. So now I have this. Velocity of A squared over the velocity of B squared equals the mass of B over the mass of A. And since it's squared over here on the left side, I'm going to take the square root of that whole thing, and then on the other side as well. Square root cancels the squaring, and so you have the velocity of A over the velocity of B is equal to the square root of the mass of B over the square root of the mass of A. And these velocities are directly related to the rate. So this ratio, you could say, the rate of effusion of A, the rate at which gas A mixes over the rate at which gas B mixes has to be equal to or proportional to the square root of the mass of B over the square root of mass of A. Okay, notice here it's rate of A over the rate of B is equal to the square root of the mass of B over the square root of the mass of A. This is called Graham's law of effusion. Okay? So, here's a simple example. It says compare the rates of effusion of hydrogen and oxygen at the same temperature and pressure. Okay? So we want to compare them. We don't need to necessarily find the actual values. We just want to compare them. We want a ratio that shows, is it twice as much? Is it 3 times as much? Is the ratio 4 to 2 or 4 to 1 or something like that? You're not actually finding a value necessarily. So we use Graham's law. The rate of A over the rate of B is equal to the square root of the mass of B over the mass of A. And all we do is, where do we find these masses? From the periodic table. So we just take, this is the molar mass of oxygen. Remember, it's O2, 2 oxygens, 2 times its molar mass of oxygen is 16. Hydrogen is also diatomic, so 2 times 1. Oops, sorry. So it's the square root of 32 over the square root of 2, and you evaluate that and you get 3.49. It's approximately 4. So what does that tell you? That hydrogen will mix 4 times faster than oxygen if they're at the same temperature. They're at the same temperature, they have the same kinetic energy, but hydrogen is moving faster, so it'll mix more quickly. Okay? Mix more quickly. All right. That basically wraps up Chapter 11, ladies and gentlemen. Make sure you watch the video on the review questions, because I go through those review questions and I'm going to solve every single one of them. There are going to be some calculations in this chapter that you have to be able to do. Lots of calculations. So I walk through those in this Chapter 11 review, and that will be in the next video. All right, keep up the great work. Let me know if you have questions.